Good morning and welcome to Cosmic Conversations here on Morrison Planetarium's Facebook Live page. My name is Ryan Wyatt and I'm the Senior Director of Morrison Planetarium and Science Visualization. And I'm being delighted to being joined here today by Juna Kollmeier, who is the Director of the 5th phase of the Sloan Digital Sky Survey, as well as an astrophysicist at the Carnegie Observatories. So welcome, Juna.
Hi, everybody. Welcome to me.
It's a great chance for us to just get a little bit of background on you, Juna, and to chat. We've got people tuning in also, I should note, on the Open Space YouTube page. And I noticed that Alex Box, who is one of the programmers of Open Space, is actually watching in too. So we're going to be chatting a little bit, and then also talking about some of the visuals that we'll use here from the Open Space software that we use in a lot of these programs. But Juna, actually, so one thing I wanted to start out with is we're going to talk a little bit about sort of the way that theory and observation work together in astronomy. And often we talk about those as like theoretical astronomers, theoretical astrophysicists, and observational astronomers, but you kind of wed those together because your background is sort of in theory, but you're leading like one of the largest observing campaigns ever. So how did that happen?
Well, they don't let me go near the telescope. Let me just be clear about that. No, I'm just kidding. So for me, the separation of theory and observation is, it's more of a time management issue as opposed to an epistemic distinction.
Right.
So I mean, I'm just really excited about theoretical modeling and also really excited about experimental work. And I would just say that for me, I just care about understanding the material universe. And sometimes you need to do some math to figure that out. Sometimes you need to, have a huge survey to figure that out. And it's all about figuring out what the world really is and how we go about that. So I just view theory and observation as different tools in the toolkit. I do think that there are some people who just don't like using those different tools. Some people don't want to get messy with experiment. Some people don't, kind of want to live in the sort of la la land of mathematics. But for me, I like to do both, and so that's why cool. I find myself in this sort of superposition state, I would say.
Do you find this like sometimes it's observations that lead theory and sometimes it's theory that leads observations, or do you think it's more one way than the other?
In astronomy, I would say that observation has led theory more often than not, just because of the vastness, as we're going to see, of the phenomenology and just the scope of it. But of course, there are punctuated points where theory has completely led the way. So if you even take examples, of course, we always think about general relativity, but even that was sort of inspired by observational anomalies. The one that I think is most in this vein is black holes, right? So people started thinking about black holes right after Newton's Principia came out because they were trying to understand about trajectories of things going fast and falling back to the Earth, and could you have something that couldn't escape? And so I would say in that particular example, I think theory really led the way. There was there was nothing in people's experience that would have brought them to black holes, right. But actually just kind of followed the math. So I would say it's a little column A and a little column B, but I think in general in astrophysics, observation tends to reveal that our imagination is lacking, so you gotta always follow the math, but look at the data.
Well, and of course, humanity has been observing the sky since we evolved on this planet. So I think that's kind of where we wanted to start the discussion today. So I think we have an image of a painting from a pretty well-known location on Earth.
Yeah, so this is the Room of the Bulls in the Lascaux Caves in France, and this painting is about 17 or 18,000 years old. And what I like about this is you can sort of clearly see in the upper right hand corner, you've got what looks like 7 stars, or the Pleiades. And then in the bottom left, of course, you got this big bull in the middle, which, the Pleiades are, as we'll see in a second, near Taurus. Mm-hmm. And then you've got something that looks maybe like Orion's belt in the lower left. And so this is a particularly striking example because you can imagine early peoples, they're busy trying to survive, and then they've got some time on their hands. Once you get fire, and they're trying to grapple with what they're seeing and trying to understand what they're observing in the sky. So we can always debate any one of these individual archaeological findings, and there are astronomers who don't think that this corresponds to the sky. If you go back to the sky picture, you can kind of see with your cursor where the Pleiades is, and there's Taurus and Aldebaran, and you can kind of see the horns there, and then Orion, of course, in the lower left. And so for most of us, when you see this pattern, you're like, oh yeah, that's what they were painting in Lascaux. But I think the bigger issue is just that people were trying to understand the physical world, and were trying to understand, what they were dealing with. And at that point in time, of course, understanding the heavens and understanding the cosmos was a matter of understanding when the weather would be good and when food would be available. And so it was just super deep in our kind of evolutionary track here. Yeah. And that's something that I think is we're still on that in that pursuit. And it's very old, and it's very universal. So it's, these are the French caves, but everywhere there were people, there's stuff like this.
Right. And from so many cultures around the world, and different representations that have sort of commonalities and differences. It's really amazing to see. Yeah.
And I think that, the story of modern astrophysics, and particularly what we're doing in SDSS, is a story of the universe getting bigger and bigger and bigger to humans, right? So the universe doesn't care about what we know or don't know about it. But, our world started out, pretty small, confined to the Earth. Then eventually, people, we have the sort of Ptolemaic picture of the universe where the Earth is at the center, and this is sort of the Aristotelian view with got fixed spheres of stars, and that, of course,
a representation of that too that we can show.
Yeah. And of course, that fixed sort of sphere of stars, that's not unique to Aristotle and his successors. That was something that was in other mythologies across the globe. And here's of course, this is the Earth-centered picture of the world. And I think Ryan, one of the nice things to point out here is that, before we overturn this, and of course we associate that with Copernicus, Aristarchus had put forward a theory that the sun was at the center of the world, and that the Earth was rotating, or the ball of fire was at the center of the universe, and the Earth was going around it. Of course, that was several, almost 2,000 years before this picture is made. And so
sometimes ideas take a while to sink in, I guess. Yeah.
That's right. And of course,
what I find fascinating about this image, I think I mentioned, is like Earth, like that's a pretty good Earth, like that map of Earth, because this is from 1660. So like we really had a good sense of what Earth looked like, and yet the rest of this is just like all wrong. Like it's pretty amazing.
Right. No, that's right. And I think that's another, what I like about the Aristarchus sort of Ptolemy Copernicus story is that there's always some, people agreed on this Ptolemaic view of the universe, even when there was another model that actually was better. And it took it took 2,000 years to figure that out. And I always just, in the back of my mind, that's a lot of generations. What ideas do we have now that we're so confident in, we're so confident about, but actually are so incorrect?
What's our geocentric baggage that we need to get rid of?
What is our geocentric baggage? And I think, and you're going to see this too, when we talk about just the size of the universe and how people struggled with that even 100 years ago. So you don't have to go back to the ancient times to find that people did not really appreciate the scale and scope of the universe, and I think we still don't appreciate it.
Well, we can switch back to our digital universe view with open space, and I've kind of kept us close to Earth, but now I can pull away to reveal our very specifically heliocentric perspective. Excuse me, the sun is kind of at the bottom of the screen, but as I pull away, we should see that come into view. Up a little bit.
Yeah, so as we're going to pull out here, get out of the solar system, you can see the Milky Way coming into view, appreciating that, that the sun is just one of, vast swath of stars in the galaxy. And then if you're pulling out of the galaxy entirely, just looking at the Milky Way itself, just realizing that, we're in the outskirts of the Milky Way. We kind of are in the suburbs. The density by us is not super impressive. The big city is 35,000 light years away.
Yeah.
And there we are kind of in the outskirts. And I think figuring out about our place in not just the Milky Way, but in the broader cosmos that's the name of the game. And that continues to be the name of the game. And it will be the name of the game for the next little bit here as well. So one thing I should say is that what part of what we're doing in the Sloan Digital Sky Survey is trying to assess where, space is. And then that's been a huge aspect of what SDSS has done, both the Milky Way itself and then externally with the galaxies and quasars, and we'll show that in a little bit.
Well, I think we can start to talk about where this story of kind of expanding the size of the universe started by kind of shifting our focus over to the Andromeda galaxy. So if we leave Milky Way behind, do not be distracted by the multicolored dots. We'll talk about those more in a moment. But to get us
next stop, Andromeda.
Right, just a couple million layers away here to Andromeda.
So Andromeda is super important because, again, we and this is a beautiful picture of Andromeda that we now have. We can see. We can see the spiral structure. We can see its companions. We can see all of this structure. And the big question 100 years ago was: is this thing, which they couldn't see very clearly 100 years ago, is this thing like the Milky Way? Is it an island universe like the Milky Way, or is it kind of more like a group of stars or some type of a ionized nebulae within the galaxy?
Well, they were called spiral nebulae for many years, right? Just as a sort of catch-all term, like whatever that means. They used the word fuzzy rigorously in 100 years ago. So this is another example of one of these common misconceptions, right? That people have, and of course. When this great debate happened 100 years ago, people were arguing two things. They were arguing about the size of the Milky Way itself. So was the Milky Way super big, or was it super small? And were these spiral nebulae inside the Milky Way or outside of the Milky Way? And the interesting thing is that, and this was the famous debate between Curtis and Shapley. And the interesting thing there is that they were both right and they were both wrong. Right.
Okay. Yeah. So Shapley is arguing that these spiral nebulae are outside of the Milky Way, obviously. The Milky Way is not that big, and these things aren't that big, and it's no big deal. And they have to be far away because at that time, Henrietta Swan Leavitt had figured out about the relationship between luminosity and distance, and so from the Cepheid stars, and so it was like, these things are far away, like, let's just move on. And of course, Curtis was like, the Milky Way is huge.
Yeah, right.
Or maybe I have that reversed. But
yeah,
the Milky Way is big, and these things are inside the Milky Way, right? And they both suffered from the same confusion, and that was that the size of the whole universe couldn't be that big to accommodate both a big Milky Way and an external Milky Way that was huge. So it was the size of the universe that was the common block that they both shared.
That's so
so I don't, So in terms of, and of course the thing that solved this was Edwin Hubble's observation from Carnegie's Science Telescope, which we see here. And of course, this now shows what Andromeda was looking like 100 years ago. And you could see it's not so obvious that it's a Milky Way. It just looks like a smudge.
Right. You gotta fill in the details if you're looking at that.
Yeah. And so you can see in the upper right-hand corner, Hubble had previously marked something N for nova, which would have been, a star that was brightening in the Milky Way. And then he crosses it out, and you've got that big red var. It's a variable, and that puts this object. First of all, it changes the whole size of the universe, right? Because now Andromeda at its proper, or puts Andromeda far away and puts it outside of the Milky Way, and also then establishes the Milky Way is indeed very large, and so is this thing. So red here, and of course this is the basis for Hubble's distance redshift relation, which is what he called it. Also the expansion of the universe. So once you have the distances and you have their velocities, you can make this, you can plot one against the other, and you can show that the galaxies are receding away from one another and that the universe is expanding. And so this is one of these situations where it's a super uncomfortable moment for everybody because the world has gotten so much bigger. The universe has gotten so much bigger than people had appreciated. And not only is it much bigger, but it's also dynamic. And so it's even uncomfortable for theorists, right? Because theorists were really into a kind of static universe that could be understood and written down, and the dynamic universe. Of course, we now know lambda. We now have the accelerated expanding universe. But at this time, the universe was small.
And this is a clear case of observation leading theory then, because you've got this set of observations that you've just got to grapple with. The other thing I think just is worth noting, because
it depends on who you talk to, right? I mean, the people who were solving the people who were solving the equations of general relativity, and people like Lemaitre and Friedman, Alexander Friedman, they were like, what are you talking about? This is how we thought it should go. But
so it's almost like matchmaking at that point. We've got these observations, and look, there's this theory that actually goes really well with that.
So I think at this point, but I think the point is really what people understood viscerally about the size and scale of the universe, and not what the difference between physics and mathematics is universes that can be. Physics is the universe that is. So when you find that the universe that is doing this crazy stuff, that is that's unsettling, I think, for people sometimes. If you like to sometimes live in the world of mathematics, it's not a problem at all. And that's why I also, going back to what we opened with, that's why I think it's important to kind of cherish both of these pursuits, because you really miss out if you're only focused on theory or focused on experiment.
Yeah. Actually, going back to the plate for a moment, I think just one thing that's kind of interesting about this, because we're seeing this, which is really basically a photographic negative. So it's the bright center of the galaxy appears as the black blob in the middle. But I guess it's what I find really amazing about this is, like, this was a physical object, like that Hubble wrote on, crossed something off, and wrote something else. Like, and it's so, in our digital era today, like, it's so hard to kind of wrap your head around, like, just the physicality of this. I think is very, very interesting.
Yeah, I mean, astronomy used to be for thousands of years a pretty rough pursuit, in that we're sitting in the cold all night long trying to
Right.
so the dedication was very high. Now, and now what we're so much, we're so spoiled by technology and by just our augmented senses that now it's still challenging, but in a not as much in the way that it is. But I mean, okay, you spend decades working on a spacecraft, and then it launches and it blows up. Like, there are different types of trauma that astronomers deal with, other than being cold, every now and again.
Well, I guess now we should actually explain maybe what all these.
Yeah. So Hubble's discovery involved less than 50 galaxies. He had to throw away a few galaxies where he couldn't get good spectra. Yeah. And part of what has happened from that moment on, that's really the first galaxy redshift survey. Mm-hmm. And from that moment on, it's getting more galaxies, understanding, okay, what is this expanding place about? What is the diversity in the galaxies themselves? And so what we're looking at are, over time, how humans have done this, and SDSS was an important player in this, in sort of industrializing this. But of course, there were other redshift surveys that were finding things before SDSS, and in particular, it motivated SDSS, in fact. And in particular, when you start doing the first redshift surveys with kind of 1,000 galaxies, you start to see that these galaxies are not smoothly distributed all over the place. They are all over the place, but they're clumpy.
Yeah.
They're in groups. And now people knew about clusters of galaxies from way back in the day, but the idea that the whole structure of the universe itself was clumpy like this, that was surprising, and that was informative, right? So you can look at this structure in great detail and figure out about things like, so this isn't just random. Right. What this is this is the structure that's set up by the dark matter itself, and the sort of scaffolding that's holding up, these galaxies live in these overdensities. So galaxies, if you throw a dart in the universe, you're gonna eventually hit a clump of galaxies. There's a lot of things too.
Each individual dot that we're showing then is an individual galaxy, and so
yeah. Really, so every dot in this video is, in this thing that we're seeing, every dot in this video is something like a Milky Way or an even bigger galaxy. Right. Typically, there's some smaller ones too, but the Milky Way is a very typical galaxy. Andromeda is pretty typical as well. It's not so typical to have Milky Way and Andromeda right next to one another, so that's kind of interesting. But every single galaxy here you're looking at is every single dot here is a galaxy, or I think, are the quasars on yet? Or
not yet. I can pull back farther. I kind of stuck relatively close to home, but we can pull back and actually show more of the Sloan data here.
Yeah, so those early surveys really motivated, that clumpiness of those early surveys really motivated, okay, what is this structure really looking like? And now you can see, as you pulling out, now you see this structure, but you also see there a more homogeneity, right? Because we're looking on a scale in which you do have homogeneity and isotropy. So the Copernican principle.
And probably worth noting that the universe isn't actually like shaped like an hourglass.
Yes. Yes. So what you're seeing there in that structure, so where you see dots, that's where the survey has happened. And where you see nothing is where we have not taken observations. And so that is where you have a hole in the mapping, in the map itself. So it's like a bit of the map has just not been made yet. And hopefully we will eventually.
Where the sea serpents would have been on that like map.
That's right. But yes, the universe is not hourglass shaped. But this, so now you can start to, and if you pull back really far, and then we turn off the galaxies, we can see, and of course there's also quasars in here, and quasars are creating supermassive black holes, and those are in the centers of big galaxies. And so now we're going to pull out to sort of early. So Stephen, that's exactly right. So the clumpiness of the galaxy distribution is indeed related to the density of the dark matter in our current best cosmological model. Overdensities in the dark matter lead to overdensities in the baryonic matter, and that ultimately allows the universe, not us, to form galaxies. And that those overdensities they're imprinted very early on in the history of the universe. So what we're looking at now is the cosmic microwave background, and you can see there's red dots and there's black dots, and they have different intensities. And this pattern of now mostly the cosmic microwave background is extremely, extremely smooth. So the difference between a red dot here and a black dot here, it looks very dramatic, but actually it's, in temperature, it's, a part in 100,000. So these are tiny, tiny, tiny fluctuations in the intensity of the cosmic microwave background. And those are the tiny, tiny little seeds of all of that structure. And so by analyzing that structure and by analyzing this structure in great detail, we can figure out about, okay, how much dark matter is there? What are the properties of it? What's the history of this is the thing that tells us that inflation had to happen. Now we'd like to understand, okay, let's learn more about that inflationary period in the history of the universe. And this is the closest that we get to direct probing of the Big Bang. This is the last scattering surface. Or the era of recombination of the universe. When the universe is cool enough that hydrogen can actually come together.
Very cool. All right.
So now, yeah, I don't know if are we gonna
just go ahead and head home? Yeah, can do that. Let me just bring some of those galaxies back on so that we can see as we head back in.
And I should say that it was Shapley who thought the Milky Way was big, and Curtis who thought the Milky Way was small, and that
I always get that confused.
They were both right. They were both wrong. I don't know.
Sorry, I'm just going to make one little adjustment here to make sure that we head home.
Well, we could look at this for hours. I mean,
it is. It's pretty captivating. Well, I guess what's interesting too is that although we're showing the locations of the galaxies with these individual points, the clusters of galaxies are also, they're held together by dark matter. There's all this hot gas. It's like there's a lot of stuff going on here.
There's a lot of stuff going on here. There, in terms of the, in terms of what this, there's a beautiful. This is where observation can often lead theory. There's incredibly rich phenomenology that occurs in every star in every one of these galaxies.
Right.
And so, so if you're interested in weird things, then astronomy is for you, because you're just always populating those weird tales of any distribution, because there's so many, nature is able to make so much, so much rich phenomena. But as we kind of come back, I think it's worthwhile to show, now you can see we're getting back to the Milky Way. And here you see these spikes again. and that's the stellar survey of SDSS, the apogee surveys, and that's about 700,000 stars where we've gotten spectra for them. And of course, getting spectra of all these objects is critical for understanding what they really are and how they work. And you can see that this is the state of the art. This is SDSS now 3 and 4, and this is the state of the art for surveying the Milky Way spectroscopically, with real spectra. And in SDSS 5, I mean, you can see how, that's all centered around the Earth because that's where our telescope is, that's where we are. And in SDSS 5, we're going to go from 700,000 of these spectra to almost 6 million of them. And the important thing is that we're going to be going to the other side of the galaxy. And so just to give you a sense of how much more there is for us to learn, even about our own galaxy. And the nice thing is that the lessons that we learn in our galaxy are transported into other galaxies. Sam has a question. How do we know what the shape of our own galaxy is? This is such a good question. It's actually really hard to figure out the detailed shape of the Milky Way because we're sitting in it. We actually look at the distances and the kinematics of stars and gas in the Milky Way to figure this out. And we look at it in optical wavelengths, we look at it in infrared wavelengths, we look at it in radio wavelengths, we look at it at X-ray wavelengths. So we have to put this big puzzle together. People still argue over the detailed structure of the spiral arms of the Milky Way. We're still figuring out about that structure. So we know from the motions of stars about the Milky Way's rotation curve. We can measure those things, and so we can understand the structure. But in fact, there's, and we can see the bulge of the Milky Way, and we can probe the dynamics of the stars in the bulge of the Milky Way as well. But in fact, understanding, it's much easier in some respects to see the detailed structure of Andromeda, which is kind of presented to us in a very nice, way, compared to the Milky Way itself. So the Milky Way is tricky, but through all of these different probes, we're able to figure out that yes, there is rotational support in the center of the Milky Way. That is, it looks like kind of spherical, but even that structure where we debate about. And then you have certainly a disk of stars. You can also, there's different clues about the chemistry in the stars look different depending on where the stars are in the galaxy. So the halo stars look on average different than the stars that are in the disk of the Milky Way, and that's because those halo stars haven't been enriched as much in heavy elements as the stars in the Milky Way. So that's a great question.
The halo stars would be partly mapped by apogee here as the stuff that's sort of above and below the plane, and I guess also the stuff that's farther away from the center.
So you can have halo stars. You can have halo stars above, below, in the plane. You can have them everywhere. Mostly the plane has, by number, they're mostly disk stars in the plane, but you can also have halo stars there. The Segway survey, which was kind of in SDSS 2 and the Segway 1 and 2. In SDSS 1 and 2, they looked at stars as well. And those stars were really focusing on the halo. And that's because they were so focused on mapping all those galaxies. And of course, the original goal of SDSS was to get 1 million redshifts for external galaxies. So we've gone in 100 years from 50 redshifts to 1 million redshifts. So that, humans are, pulling our weight. And we want more. we need more. But anyway, those stars are preferentially outside of the disk. So the disk is really disky, and that's of course because of angular momentum and the dissipation of that into a disk where the stars form, and that's where they kind of stay. But there are stars. There's the Milky Way has all there are stars from the disk that can get pumped up to higher distances above the plane. But typically, if you want to find halo stars, you look away from the disk. But the halo stars are just, kind of think of a spherical distribution of stars that go out very, very far away from the disk.
I think it's amazing too to hear about, and Apogee, I think, is part of this story, as well as Gaia, which we've talked about in previous conversations. But it's like just between the chemistry and the motions of the stars, being able to kind of play back and even learn more about the history of the Milky Way and how much we're figuring out about that is just, it's kind of mind blowing.
So the thing that has been, and Gaia is just incredible. Because Gaia is really pinning down a lot of the positions now of, billion stars. And so, Gaia is incredible because that just gives us these basic parameters of the Milky Way. Right. What I think is just so fascinating is that if you even look back 20 years, okay, the idea that we were going to not just be probing the center of the sun with the technique of helioseismology, but that we were going to be probing not just the centers of a handful of stars with the technique of astroseismology. This is similar to seismology on Earth, where you got an earthquake and figure out about the structure of the Earth from looking at the oscillations at the surface. Now we can use this technique and combine it with spectroscopy to figure out ages of stars across the entire galaxy. So the idea that we're going, we have ages for 500,000 stars, and we're going to have ages for millions of stars. We just have these cosmic clocks all around the Milky Way. That was if you had put that on a wish list, maybe 30 years ago, it would have been seen as like a really ridiculous sort of wish. And now it's happening. And I think that's a testament to people's creativity. It's a testament to sort of cross-disciplinary learning, where people in the machine learning and deep learning communities talk to people in the astronomy community, and different surveys talk together about how to make these things all work. And so I think it's really the story of how our information, it's one of the good stories of how this sort of information overload age is enabling us. In many ways it's disabling us, but in this way it's really enabling us. And that's just incredibly exciting, because in our theories we can predict the time evolution of things pretty well, but in observations it's often very hard to unravel things in time. And this allows us to do that with the Milky Way.
I guess it's kind of interesting too, because when you think about where we started the program with K's Lascaux, and time was a much more cyclic phenomenon then, because it was kind of like the seasonal change, and like you said, the way to predict when the weather's going to change, and that sort of cyclic, repeating in a certain way static universe, compared to now this very evolving and temporally exciting universe that we live in.
No, we've gone from sort of a fixed world, either on our cave or in a glass sphere, or you've got the Egyptian newt, or you've got, we've gone to sort of a fixed ceiling of the universe to this incredibly dynamic, infinite world, which is both very humbling and very exciting. And I think, just the idea, I just think about it, there's just a new sky every second of the day. It's different. Something is going off, something is exploding. We've, gotten a little bit bigger. I think that's a very just intoxicating picture of the world. And it's also very humbling in terms of what our place in the universe is. It's just amazing that in this relatively, in terms of cosmic time, like let's go to now is just nothing. Just nothing at all. And we've been able to figure out so much, and there are still these huge, huge mysteries. I certainly hope that my great grandkids are going to be like, yeah, they used to talk about dark matter and dark energy. Oh my gosh, they were so cute and silly. I certainly hope that they will look back at us with that type of disdain for our ignorance. I just hope that that's the arc that we're on,
Right.
but also appreciation for
Yeah.
our attempts.
Absolutely. Well, if we don't have any other questions, I don't see any more coming through. So I think just thank you very much for taking some time and sort of chatting with us today and flying through the universe and having a little conversation about how big and changing the universe is.
Thanks so much, Ryan. This was a lot of fun. Thanks, everybody, for tuning in.
Yeah. All right.